So, hey nerds, this is Suman, and this is our today's topic of interest, the kinetic energy. And we all know the thing about it. It is the energy associated with the particle when it is in actually motion. So, the m be the mass of that particle moving with some velocity v, and if you divide it m over v square by 2, you get the corresponding kinetic energy term. So, this is the everything that we had learned or simply memorized during our junior classes, right? But I would like to show you something very much beautiful thing about it, and you would might know, and some of you might know this already, and some of you might not have known this already. Yes, and this is going to be our today's agenda, right? So, if I assume the fact that if I assume a fact that mass is constant, so you can take the mass as 1 kg and you can accelerate the particle with some different kind of velocity with 10 meter per second, 20 meter, 30, 40. So you will get the corresponding different kinetic energy. So from here you can see that the energy is proportional to v squared. And this is actually, if you plot a graph of kinetic energy, so the energy versus velocity graph, you will end up getting a parabola. So this is the graph that the relation is predicting to us, right? And this is all we know. Suman, we all know that this fact. So tell us something very much different. So I would like to show you something very much different here. That I got my energy term is 1/2 mv squared, and since my mass is constant, the variable part is just the velocity. So I can write energy as function of velocity can be written as 1/2 mv squared, right? Yes, Suman, you are right. So most of the people might interested in the slope of this graph, right? So in order to evaluate the slope of the graph, we have to differentiate our two variable term, that is energy with respect to some velocity term, right? So I would like to differentiate it. So I get dE over dV can be written as 1/2 m dV squared upon dV. So I get 1/2 m 2v, and I got mv, or simply the momentum. So the rate of change of energy with change in velocity. So the energy change per unit change in velocity is nothing but the momentum of the particle. So this is the very much interesting thing you might not know, right? Or you haven't seen through this equation. So if you want to be interested in any point of here, suppose for this point, if you take a slope, if you draw a tangent to this line, you will end up getting the momentum of the particle in every point, at every point. So even at this point you will get the momentum, even if you get the slope as 0, but there will be the slope. So even at this, the slope is going to be look like this, and the corresponding velocity is 0, so the momentum is going to be 0 here. So at this point, your rate of change of energy with respect to velocity is going to be 0. So this is the first thing that the relation predicts. So it is very much beautiful to me when I got thought about this. So another thing you can actually ask me, Suman, what if we differentiate this term again with respect to velocity? So let us do that also. So I have rate of change of energy with respect to velocity is my momentum. So again, the rate of change of velocity is function of velocity since my mass is constant. So I would like to differentiate it. I got d over dv, dE over dV, I get m dV over dV, and I got a simply m. So this can be written as d2 E over dV2 can be written as the mass. So this is the mass, and the second derivative gives you the concavity. So the second differentiation of energy with respect to velocity just gives you mass. It is equivalent to the inertia. So the graph, the second derivative gives you the mass, right? So how much inertia is actually present within that system. So it gives us that thing. So from here you can see that the second derivative is this much. So you can actually predict from here, the more mass you have, the more concavity is going to you have. Suppose I have different mass and I got different amount of concavity. So it is concave downward, right? So it is actually concave downward. So if I have less mass, there will be less amount of concavity. And If you had larger amount of mass, there will be more amount of concavity, and etc, etc, etc. So this is the new thing that I had learned by myself, and 2 days ago, and I am sharing it with you. So up to there, bye bye, and I hope you guys got something very much new about something physics. So you can actually do and another thing with potential energy term, and let's check whether you get concavity here or not. And if you don't get concavity, and I really know you don't get any concavity here, because the power of height is going to be linear, and the second derivative doesn't exist, or simply it is zero. So you will not get any concavity here. So up to there, bye bye.